We're recording. Okay. A sociologist believes that more boys than girls are born during wartime, right? And she's made that statement based on a piece of information. That piece of information is in 200 babies born in countries at war, 116 were boys. What do you think? Do you think her statement's a reasonable statement or not? More boys than girls, if 116 out of 200.
Well, from the data, yeah, it's true.
So it's only just over half, but it is slightly over half. So when we're doing the hypothesis test, just to remind you, what we're looking at is we're asking ourselves, is this number, I got this new little tool, is this, so I don't have to point at the board, is this number significantly above half enough to accept what she says is true? And we're going to do a mathematical test. Rather than just kind of go, that's what I think, we're going to do a mathematical test. All right? So, what we looked at was there are some formalities to a hypothesis test, and that's why I've given you that sheet printed out in red. This has kind of got examples of the kind of thing that you have to write down. Right? But we went through it and said, you've got to define your variable. All right? So P is the proportion of boys in the population. Then we have to state our two hypotheses. Now, the null hypothesis is kind of like always that there's no difference in anything. So H0, we're saying the probability of boys is a half. All right? And in this time, the woman has said, why have I assumed a sociologist is a woman? Does it say anything? I think it might say it in the question. She said that 116, well, there's more boys than girls, which assumes that the probability of it being a boy is more than a half. So that's why we've got the probability of P being greater than 0.5 is the alternative viewpoint. So that's your alternative hypothesis. We're still defining our variables, so let X be the number of boys in a sample of 200 babies. Makes sense. We are then making a statement that X, the variable X, is binomially distributed. There are 200 trials, and the probability of a boy is 0.5 from our null hypothesis. Okay, now is the time at which we've got to do a bit of a test. Have you got your notes? Have you found where you've written this from last time? So basically, what we're looking at is a hypothesis test or a probability distribution. We've got a curve like this, right? And in this question, it says, did I write it? It said, actually, I didn't put this. So we've got to do a test now, and it says in the question, does the data support the sociologist theory at a 5% significance level? Okay, so this is what we need to test. Does the data support this hypothesis? And this is an important thing, at a 5% significance level. So that's kind of introduced a new thing to you, which is significance level is basically deciding at what point is something significant or not. And normally there are the different significance levels that you will be asked to test on will be 1%, 5%, or 10%. All right. The bigger the number, the larger the zone that is significant. All right. So it might make sense when I start sort of talking about it. So what does a 5% significance level mean? Well, we've got a region up here, and this area, which you've already done, right, with the binomial distribution, that region there represents the probability of something happening. So at a 5% significance level basically means that this is a 5% area, 0.05. All right? And we are going to look at the test statistic for 116. And we're going to find out whether the probability of it being 116 is less than 5%, therefore in this region, or more than 5%, which means it's in this region. Does that make sense? Yeah? So, what we're going to do is we've got to test our test statistic, which is x equals 116. Right. Now you might be thinking, well, there's two ways of doing this now. I can find the probability of 116, or I could figure out what the value is here. But let's try both. Okay. All right, so we've got to work out that the probability that x is greater than or equal to 116. So what is the probability that we have 116 boys if normal is a 50-50 split? Does that make sense? So how do we do that? Now, on your calculator, right, do you know how to use your calculator to do this? Two ways to do it. Have you all got this distribution app on your calculator?
Yep.
Right. If you don't, you can go online and update your operating software on the Casio website. It's worth doing it, and I'll show you both and you'll understand why. So if you click on distribution, obviously we then want to select binomial. Now the tail, we'll talk about a different option. The tail is which side of the line do we want? Now we're testing for the area is above. What's the probability that we're above? So if I select this one here, so that means press F3. All right. Am I who's got this version? Just you two. Okay. I'll do it quickly and then we'll go through the other way then. So if you can all follow, because you would do update your software.
Sure.
Yeah.
So,
So what?
the
So if you're in menu,
yeah.
normally you're at this level. Scroll down and go to distribution. Hopefully, if your calculator is relatively new, you should have it. Press exit, execute. Make sure the tail, that if you press that way, we're testing for x is less than or equal to. If we're doing that, x is between two values. This one is x is greater than. So we want x is greater than and x 116. Look. So I press enter and I get this. If I go back to exit, I can change these. So 116, number of trials is 200 babies. The probability of it being a boy we're saying is 0.5. Go down, press execute, and you get the graph. So you can see that little region, right? So that is the region that is the probability of there being 116 boys, given that it's a 50-50 chance. So what is that probability? Well, up here it says, look, 0.014. Make sense? So if I write that down, I've got 0.014, okay? Which means on my diagram, is 0.014 more than 0.05 or less than? So 0.014 is less than 0.05, which means it's going to be in this region. So 116 boys is in that critical region, which means it's not very likely to happen. So if the probability of boy and girl is 50-50, getting 116 boys out of 200 is only 1.4% likely to happen. All right. Now, can you see there? This is from a 5% significance level. So what would happen if I changed it to a 1% significance level? So this black line would actually be the other side. So it would actually change my conclusion. Does that make sense?
Yeah.
So the significance level actually can change what our result is. So how significant do we want this difference to be, you know? 10% would give me all the way up to here. You know, it would make it even less likely to happen. So it'd be more in. So we're in that region anyway. Yes.
What's the whole percentage?
100.
100%.
The area under the entire graph. So remember, you've done here halfway, obviously, is 50%.
Yeah.
I've gone quite over the top here. 5% should only be a little bit. If you look at the calculator screen, look how small 1.4%, 5% would only be up here. All right. Now, so we have decided that 0.014 is less than the 0.05. So what is my final conclusion then? What would you say based on what her statement meant when? Her statement was she believes that there are more boys born during war than girls. What has our result decided?
That it's possible, but it's unlikely.
Okay, so does that support her claim or?
Yes, because her claim was like a statement.
Yeah, so she's claimed that more boys are born. Now, if we go in with the view that the probability is 50-50, then if 116 was quite likely in a 50-50, our probability would have been quite high. But because we've got a probability that's really low, it's only 1.4%, and it's in that critical region, we're basically saying she's right. 116 is not very likely. So this is how we need to finish off our answer, which is, we say, because 0.014 is less than 0.05, okay, there is sufficient evidence, and this is a kind of formal approach, you have to write it like this, there is sufficient evidence to reject H0, the null hypothesis. All right. So we've just discussed why that is, and we would finish with at the 5% significance level, all right, there is evidence to support the claim. All right. Now, as I said, you might be thinking, well, that's a lot of writing, but yes, it's a hypothesis test, so there is a formality to your answer. And one thing is, I'll put a little note here, must put it in context. So that's this line here. So you must make the statement. Are you accept it? No, actually we don't say. Are you saying we have evidence to support the sociologist's claim, or are we not? Okay. Now you'll notice I again said we don't ever accept she is correct. Do you remember why? We're not saying she's right. We're just saying at the moment we don't have enough evidence to say you're wrong. So we never say anything is definitely accepted. We reject the null hypothesis, suggesting we have evidence to say she might be right, but we never actually say you are definitely right. So, in the last general election, Party Z won 36% of the vote. An opinion poll surveys 100 people and finds that 45 support Party Z. Does this provide sufficient evidence at 10% significance level that the proportion of voters who support Party Z has changed? So there is something a little bit different about this one compared to the other one, and it might be a little bit subtle to start with, but it just says here, it says, does this provide sufficient evidence? We've got the 10% significance level, but the big thing about this question that's different is it just says, has it changed? Okay, whereas in the previous question, all right, she was saying something specifically different, which was more boys than girls. So we had a hypothesis, an alternative hypothesis that the probability was greater than 0.5. So, yeah. All right. Now the difference between that and this one, okay. So that previous one was a one-tailed test. This, because it just says changed, it doesn't say changed up or changed down. This one is a two-tailed test. So what that means is, if we consider the diagram like we did before, we actually have two regions to consider, which is we have a region at this end for more than, but we also have a region at this end for less than. So the previous one, I'll just show you the diagram again. The previous one was a one-tailed test because we were only worried about it being greater than a certain amount. But this one, because it could be greater than or less than, we have a two-tailed test. Exactly. Yes. But what is important is, well, apart from that being really important as well, this 10% gets split into two lots of 5%. So we now have just like before, we have, instead of a critical region of 10% up here, we actually only have 10% split into two is 5% this end and 5% that end. All right. So the value is 0.05 this end and 0.05 probability that end. Okay. So that's understanding the situation. Yes.
Can we just calculate
no, because we need the two different values, don't we? Yeah. All right. Let's go through the process now. So what do we have to do first in a hypothesis test? So let P, okay, be the proportion of voters supporting Party Z. So again, some of you will just forget that you just won't get straight on with numbers and write numbers and you put them all over the page and it's really hard to mark your work. For a hypothesis testing, you need to write these things down, structure. Okay, what do we do now? Well, sorry, say again?
We need to find an X.
Not yet. I mean, it doesn't really matter, but normally the next thing we state are the null hypothesis. So null hypothesis and the alternative hypothesis. So what are the hypotheses? Now you've already told me. The null hypothesis is that the probability is not changed. So what was the probability?
36%.
So 36%. So we're going to say 0.36. So the null hypothesis is the default no change. Okay. Now you were right before, Ethan, in that instead of more than or less than, we just say the probability is not equal to 0.36. And once we've stated that, so we've got P and we've defined what P is and we've said what the hypotheses are, now we can say let X be what?
The proportion of votes.
No, that's P.
Number of voters.
The number of supporters of party Z in a sample of 100 people. Okay. So then we can say X is binomially distributed. Number of trials is 100, and the probability is 0.36. Okay, so now it's a bit like, how do we determine this then?
Put into a calculator.
Well, we've got to have some numbers to put into our calculator first, which is what was in the question. So the question says
45.
that 45.
So you probably want to put in 44, 45, 46.
Okay. So we are going to work out the probability that X is greater than or equal to 45, because our test statistic is the probability that X equals 45.
What is the test statistic?
Well, we've been given that the test statistic is the thing we're testing, which is over there, look, finds that 45 people now support. So that's our test statistic. We're testing whether 45 people is a significant enough change from 36 people. Yeah? Because it was 36.
That's the independent variable that changed during the testing. When there was something.
Yeah, so 36% of the vote, well, that would be 36 if it was 100 people, but a general election is more than 100 people, but it would be 36 out of 100. So we're now going to poll 100 people, and we now get 45 people. So is 45 a significant enough change, is what we're saying. All right? So the statistic that we're testing is X being 45. All right? So we're going to try and find the probability that X is greater than 45. All right? So how do we do that? So on our calculator, should we do it the other way this time? If you don't have this, we can go to Statistics. Okay. Go to stats.
So this isn't cumulative, is it?
Yes,
It is.
because it's greater than. Going to go to distribution. Binomial. BCD for cumulative. Okay. I don't want a list because I've not put data in, so I'm going to change that. Sorry. Execute. I need to do it here. Look, list or variable. So I'm going to change that to variable. Now I want greater than 45 or equal to. So my lower bounder is going to be 45, and my upper is just going to be a really big number. So I'm going to put 1 times 10 to the power of 99. Kind of basically go, because the graph goes on forever, yeah?
Well,
Basically to infinity.
You could just put it at 101, right? Because it's out of 100.
I guess,
Is that
technically. But you still kind of miss a little bit of just the way it's sorted out. I mean, you'd be fine. You just need to pick a big number.
Okay.
Common convention is we put 1 times 10 to the 99 for an upper bound, or minus 1 times 10 to the 99 for a lower bound. Okay. We're going to put the number of trials as 100. The probability is 0.36. Execute, and we get a p-value of 0.397.
0.0.
0.0397.
Get that, sir. 0.03. Wait.
So what does that mean?
It's smaller than.
So 0.0397 is smaller than 0.05. So if we consider our diagram, where does that put it? Well, it puts it either here or here. Okay? So, now can you see how this question would, actually probably wouldn't if you did 10%, it would be still fine. But what's our final conclusion then? How do we finish this question off? So we can say, so there is sufficient evidence to reject H0, and then to put it in context, there is evidence, okay, that the proportion of voters for Party Z has changed. Now, I have mentioned that there's a formality to these hypotheses. You have to write things out. Now, there is a bit of leeway to it, which is it doesn't have to be perfectly written like every single time, but as long as you put it into context, like, so this suggests it has changed. You know, if you just put, you have to say, I'll use my little laser pointer, you have to point this bit out, and you have to say evidence to reject that, but then you can say, therefore, voters for party has changed. You know, you can, especially if you're in an exam situation and you're running out of time, just make sure you've got your point across. Okay, but remember this bit here is in context, so you're showing that you do know what that means in terms of voters. Now, obviously, you can lose out because if you said, would it be correct if I said there is evidence that the proportion of voters has increased.
Oh no. No, because it's changed, not increased.
Good, because it's also saying it might have got down. Like, you know, there's just evidence to say it's changed. We can't say it's gone up, or we can't say it's gone down. We can say it's changed. It's not what it was before. All right. So be careful about just the details.